Hello, everyone. My name is Mojtaba Hosseini. I'm a PhD candidate at the Paul Merage School of Business at University of California, Irvine. This is a joint work with Vijay Vazirani titled Nash-Bargaining-Based Models for Matching Markets, One-Sided and Two-Sided, Fisher and Arrow-Debreu. So I will start with an overview of matching-based market design and the Nash bargaining game in general. Then we will see some connections and comparison between High-Lanzig-Hauser scheme and Nash bargaining-based models. I will talk about our proposed one-sided and two-sided Nash bargaining-based models, followed by two solution methods for solving these problems. And finally, I will conclude my talk with some computational experiments. So matching-based markets are different from the usual commodity-based markets in the sense that they are not necessarily driven by price. And these are matching markets because neither side can simply choose, but also needs to be chosen. So classical examples of matching markets are, for example, matching students to schools or residents to hospitals and so on. But recently, with the recent innovative matching markets such as AdWords, Uber, and Airbnb, these applications have led to a major revival of the area of matching-based market design. But a general issue in this area is a lack of models that can use cardinal utilities. To address this issue, we propose Nash bargaining-based matching market models. So assume that we have n agents and n indivisible goods, where each agent I has $1 to spend and has a utility uij for good j. So the prominent solution based on cardinal utilities is the High-Lanzig-Hauser scheme, which creates a parity between supply and demand using a pricing mechanism. To use the pricing mechanism, HZ assumes that goods are divisible by assuming that there is one unit of probability share of each good. Then HZ finds a fractional perfect matching of goods and agents, as well as a price for these goods to find equilibrium. HZ enjoys some nice game theoretical properties. For example, it satisfies Pareto optimality and envy freeness, as well as incentive compatibility in the large. But a major drawback of this scheme is its lack of computational efficiency, which then makes these nice properties of limited applicability. An n-person Nash bargaining game consists of a pair N and C, where N is called the feasible set, is a compact and convex set, and its elements are vectors whose components are utilities that the n players can simultaneously accrue. There is also a vector C, which is called the disagreement point, and its components are utilities which the n players accrue if they decide not to participate in the proposed solution. We say an instance NC is feasible if there exists a point V such that the utility of agent I under V is strictly better than their disagreement point. So the solution to a feasible instance is the point V that satisfies the following four axioms. The first axiom is Pareto optimality, which means no point in N weakly dominates V. And the second is symmetry, which in the sense that if we renumber the players, then a corresponding solution to the new instance would be the one that we renumber the coordinates of our solution V. Also, the third axiom is invariance under affine transformation of utilities, meaning that if the utilities of any player is transformed with some affine transformation, then the solution can be up to the new instance can be obtained by the same transformation. Finally, the fourth axiom is independence of irrelevant alternatives, meaning that if V is a solution to instance NC and S is a convex and compact subset of N, such that it contains both the disagreement point C and our solution V, then V is also a solution to this instance C. Using an elegant proof, Nash showed that if the game NC is feasible, then there is a unique point in V in N that satisfies these axioms. Also, it turns out that this point is the solution to this maximization problem, where we maximize the product of the difference between the utilities of the agents and their disagreement points with respect to V belonging to the feasible set. And we can, in fact, turn this problem into this convex problem and find the solution to the Nash bargaining game by solving this one. And since it is convex, then it can be solved efficiently. With Nash bargaining-based models, we sacrifice some properties of the Highland-Zeckhauser scheme, but we gain efficient solvability. Obviously, these nice properties of HZ have little meaning without solvability. So with our approach, we yield a plethora of matching market models. These models range from not only one-sided, but also to two-sided models, as well as Fisher setting and Arrow-Debreu setting. And the utility functions range from linear all the way to Leontief. Okay, so to see some connection between Highland-Zeckhauser scheme and Nash bargaining-based mechanisms, we first pay attention to our shift from pricing mechanism to a Nash bargaining mechanism. So we have proposed a shift from a pricing mechanism to a Nash bargaining-based mechanism for matching market models. And this shift arises two questions. The first question is either type of mechanism reducible to the other? And the answer is no. In fact, we can easily verify that under an affine transformation of the utilities of agents, as we just saw, the Nash bargaining solution undergoes the same affine transformation while an HZ equilibrium remains unchanged. So they are not reducible to each other. The second question is this shift a principled one? And the answer is yes. In fact, there's a fundamental connection between these two mechanisms through the linear Fisher unit demand problem, or LFUP. In this problem, we are concerned with finding a fractional perfect matching between agents and goods when agents have linear utilities. So if we solve this problem using a pricing mechanism, we derive the HZ equilibrium. And if we solve it using a Nash bargaining mechanism, we derive 1LF, which is our most basic Nash bargaining-based matching market model. And I will talk about it more next. Okay, so we propose several Nash-Bargaining-based models categorized under one-sided and two-sided matching markets. Under one-sided matching markets, we start with our most basic model, which is 1LF, and we have Linear Fisher Nash bargaining Y-sided matching market. We then we will see our next model, which is linear Arrow-Debreu Nash bargaining one-sided matching market model. We then generalize these models to nonlinear utility functions, namely separable and non-separable piecewise linear concave Arrow-Debreu one-sided matching markets. For the two-sided, we generalize our one-sided to two-sided, and we call it 2LF, which is under the linear Fisher setting, but we can easily extend this setting to the Arrow-Debreu and non-separable and separable and all other utility functions. Okay, so our linear Fisher Nash bargaining one-sided matching market, or 1LF for short, is our basic model, and its standard application is in matching agents to goods. So here, let's define some notation. X denotes the set of fractional perfect matchings, and each agent I has a utility for good J, denoted UIJ, and under a given fractional perfect matching, the utility of agent I would be the summation over all goods. This setting is in fact identical to the Hyland-Zeckhauser setting, but the difference is that the definition of solution to an instance is different between these two settings. We solve this problem using a Nash bargaining mechanism by solving this convex combination, convex program given here. Our next model is a linear Arrow-Debreu Nash bargaining one-sided matching market, where on top of what we had for our Fisher model, we also have a disagreement point C, which is not necessarily zero. And for example, it may correspond to an initial endowments of the agents. We also assume that the instance is feasible in the sense that there exists an allocation under which the corresponding utility of each agent is strictly greater than her disagreement point. And this model is applicable when agents start with an initial endowment of goods and then change them to improve their happiness. And we can cast it as this convex program here. Note that this disagreement point appears in the objective function, and if we set Ci to 0, then we get our 1LF model. To generalize to nonlinear cases, we first consider the separable piecewise linear concave utility functions, which is analogous to our 1LAD model, but with the difference that the agents have separable piecewise linear concave functions, Fij. Each of these functions are represented by some segments. Each segment K has lengths Lijk and a utility rate Uijk, which agent I accrues utility per unit of good J received when she is getting an allocation corresponding to this segment. With this definition, the total utility of buyer I would be simply the summation of these functions over all goods. And we can cast this problem as this convex optimization problem. Note that here our X variables have 3 indices, one for the agents, one for the goods, and one for each segment, for each pair of agent and good. Our second nonlinear model is the non-separable piecewise linear concave utility, abbreviated 1-NAD. And it differs from our previous model in that agents' utility functions are now assumed to be non-separable. These utility functions are very general and can be used to, for example, capture whether goods are complements or substitutes and much more. So we can consider utilities of this form, and a special case is the Leontief utilities, under which agents want some goods in specific ratios, and this model is suitable for modeling utilities when goods are complements of each other. With this definition, we can find the optimal solution by solving a convex optimization of this form. It is natural to assume that each side has a utility function over the other. Therefore, we also consider a two-sided version of our matching markets. The simplest setting being Linear Fisher Nash bargaining two-sided matching market. In this setting, our goal is to find a perfect matching between agents and jobs, where both agents and jobs have linear utility functions. In keeping with the axiom of symmetry under Nash bargaining, we posit that the desires of agents and jobs are equally important. Therefore, our feasible set is now in a 2n-dimensional space, where each utility vector V consists of 2n elements. The first 2n elements correspond to the utilities of the agents, and the second elements correspond to the utilities of jobs. And similar to our other models, we can cast this model as a convex optimization problem of this form. To solve these problems, we present two solution methods, namely central cutting plane algorithm and Frank-Wolfe algorithm. Both of these algorithms rely on linear approximations of these problems and converge to the optimal solution in polynomial time. But to obtain fast implementations, we need some new ideas beyond the standard methods, where we enhance these methods with tailored to our specific problems. And I will talk about these enhancements as well. Our first algorithm is the cutting plane algorithm. Let's say FV is the objective function of one of these models. For example, let's say it's the objective function in 1-LAD. Since the objective functions are concave, we can show that F is upper bounded by the hyperplanes at each arbitrary point we had. Using this relation, we can reformulate our optimization problems as semi-infinite linear programs of this form, where eta is replaces the objective function and is upper bounded by these hyperplanes for each trial solution we had. Since this formulation contains infinitely many constraints of this form, a natural way of solving it is to replace this feasible set with a manageable subset, let's call that n hat, and then we iteratively grow n hat to make this relaxation a tighter relaxation until the bounds of this problem converge to the optimal solution of the original problem. But a better way of solving this problem is to find the center of the hypergraph approximation instead of finding the optimal corner point at each iteration. With a linear program of this form, we can obtain the radius sigma and the center of the largest ball that can be inscribed inside the hypergraph approximation. And we can show that as the algorithm iterates, the radius sigma diminishes and it approaches 0, while the center of the hypergraph approaches to our optimal solution to the original problem. We also propose several enhancement techniques for faster convergence. The first enhancement is regarding cut generation. Rather than cutting off the current point at each iteration, we propose to perform a line search between the current solution and the best solution identified so far. This way, not only we improve the bounds, but also we generate more effective cuts, because this intermediate point is more likely to belong to the interior of the feasible region. A common issue in cutting plane algorithms in general is that LP solvers may have difficulties in handling the unbalanced cuts. And we call the cut unbalanced if the coefficients of the variables are very different in the cut. We propose to replace our eta, which corresponds to the objective function value, with some scalar multiplied by a new variable, so that we can scale this variable and thus balance the cut. Another issue specific to this problem is that our objective functions involve logarithm function. Therefore, they cannot they cannot have an argument where v minus ci is 0. If it happens that for some solution at some iterate of the cutting plane, if vi minus ci is 0, we cannot extract a cut from the solution. And our proposed solution is to, instead of cutting this point, we find its closest point in the interior of the feasible region by taking a convex combination of this point and some arbitrary interior point. Finally, we would like to be able to use the information during iteration T and we obtained during iteration T in the subsequent iteration. To do so, we use dual simplex method, which helps us avoid solving the LPs from scratch at each iteration. The second solution algorithm that we have, this idea behind this method is replace the nonlinear objective function f with its linear approximation at trial solutions. In our case, if we replace f with its linear approximation, we obtain a maximum weight matching problem. Therefore, the solutions that we find at each iteration are integral perfect matchings. And then the algorithm continues by doing line search between this integral perfect matching and the trial allocation that we had to find the next trial allocation. And since this step involves solving a max weight matching, it can be solved efficiently, and therefore the algorithm overall is efficiently solvable. So let's start with linear utility models for the computational experiments, namely our 1LAD, 1LF, and 2LF. Note that these models have similar structures in the sense that their feasible regions are all matching polytopes. Therefore, both Frank-Wolfe algorithm and cutting plane can handle them efficiently. We consider several scenarios here. We consider two scenarios for the utility matrices. One is where the utility matrices are bivalued, we call them binary, and the other case is where utilities are general integers, so we call them non-binary. We also consider different number of agents and goods from 200 all the way to 2000. I have discarded the smaller instances because the running times are negligible here. We have also considered different parameters to capture the sparsity of the utility matrices through this parameter rho. So the smaller value for rho means the instance is sparser. From these results, we can observe that Frank-Wolfe can handle the binary cases consistently, more efficiently than the cutting plane algorithm, while both Frank-Wolfe and cutting plane are suitable for the non-binary case, with cutting plane performing slightly better than the Frank-Wolfe, particularly in the denser cases. Now, with the non-linear utility functions, one SAD and one NAD, we have considered different number of agents and different segments for the utility functions. For the separable case, capital K denotes the number of segments for each pair of agent and good, and we have considered two numbers. And for the non-separable case, it captures the number of segments for each agent. As expected, we can observe that as we increase the number of segments, the problem becomes increasingly more challenging. But the cutting plane algorithm has managed to solve all the instances in a few minutes. But with the non-separable case, it turns out that the problem is more challenging than the separable case. And but the cutting plane algorithm solves all the large instances up to optimal solution in less than 1 hour. And but it starts to struggle for the cases where the number of segments are large. So with this, I end my talk. Thank you for your attention, and we would be happy to hear your questions.